All right, so next what we're going to do is learn how to make these free body diagrams. So in this first situation, we have a box falling, and we're going to do something called neglect air resistance. So we have this box, and it's going to be falling to the ground. And in this case, because it's falling under the force of gravity, it's going to get faster and faster and faster. So it's accelerating. So we want to show that. So what we do is we take the object that we're concerned about and we get rid of everything else. So all we have is a box. And then we also want to think about where that center of mass is, and we're going to indicate the center of mass as a dot. All right, so back to this neglect air resistance thing. What neglect means also means to ignore. And you'll sometimes see it written as the word ignore. Ignoring neglect means we don't care about air resistance in this situation, so you don't have to draw it. So let's think about our box. Our box is falling to the ground, and the force that's causing it to accelerate towards the ground is the force of gravity. So we draw an arrow going down on our box, and then we label it F for force and gravity, G-R-A-V for short. And so in this situation, all we have is one arrow going down, and we label it force of gravity. So let's look at our next situation. This time, we are going to have a box falling, but as it falls, it's going to get a parachute. And it's going to get slower and slower and slower as it goes down. So we've got our box parachute system here. And instead of worrying about drawing all of our parts to our system, we're just going to have a box. And we care about the center of mass, which is going to be represented as a dot. A lot of times we don't have the dot there. We just have our box. And there's some people who do free body diagrams, and you'll see it this way as also a dot. Both ways are acceptable. Most times we see it as a box. So we're just going to do this as a box from here on out. So notice now, in our situation, we have a box falling from the sky, slowing down. So our key thing here is slowing down. So this tells us that we have an unbalanced force. So our arrows are not going to be equal this time. So we're always going to have a down arrow. And we're always going to have it labeled gravity. So when you do these and you don't know where to start by drawing your gravity arrow. Now in this case, we do have air resistance. And it's going to be longer than our gravity arrow, because remember, our arrows are vectors and they show both direction and magnitude. And for it to slow down, our air resistance has to be bigger than our gravity. So we have two forces on this one, air resistance going up and gravity going down. And because it's slowing down as it falls, our air is going to be bigger than our gravity. Okay, so let's look at our box with a parachute situation again. This time we have a box falling at a constant speed. So this situation is going to be slightly different. So let's bring in our box again. We've got our box to represent our system here. And we're going to draw two arrows, and you guessed it, the first arrow is going to be the force of gravity. And because we have a constant speed, we do not have any acceleration. And that means we have balanced forces. So we are going to draw an arrow up the same length as our gravity arrow, and we're going to label that air. So it's very similar to our last situation, same forces, but except they are equal in length. Okay. So now we have a box, and our box has fallen all the way down to the ground, safely landed onto our ground. And so our forces change now that it's landing on the ground. As always, we're going to draw our gravity arrow. And our box isn't moving, so we need a balanced force for our gravity arrow. And so we're going to draw an arrow going up. It's going to be equal in length because we're balanced forces. Now we're going to call this norm, for normal. I like to call it norm because it's fun. So we have the force of gravity going down and the force of norm going up, and they are equal length because our box is not moving. Okay, so let's leave our box now. And this time we're going to have a car. And our car is going to be driving, and it's going to be slowing down until it gets to a stop sign. Okay, so we have a car moving to the right. Direction's important when we're on the ground when it moves, and we'll see why in a second, and we know it's slowing down. So slowing down means it's accelerating. It's deaccelerating in this case, which means we're going to have an unbalanced force. So now we're getting a little bit more complicated. Let's get our box to represent our car. And you know it. We're going to have an arrow pointing down, and we're going to label that the force of gravity. Now, our car is not a flying car. It's staying on the ground. So because it's on the ground and isn't flying, it's going to have a balanced force with gravity with normal. Those are going to be equal. So we have gravity and norm going up and down. Now what we have to think about is what is our left to right. Our situation doesn't say anything about brakes or motor, so we're going to assume that it's just coasting to a stop. And what force is slowing that down is the force of friction. So we're going to draw an arrow opposite the direction that the car was moving. This is where that right comes in handy here. The car was moving to the right, which means our force of friction is in the opposite direction going to the left. Okay, next situation. This time we have a block being pushed on a table to the left. So again, we want to pay attention to what direction it's going on and the fact that it's sitting on some sort of table. So we have our block being pushed to the left. So we're going to bring in our box again. We're going to draw gravity, and we're going to draw norm. It's not a flying block, so we're going to have our arrows be the same length, but opposite directions, so that it's balanced in that direction. And we had a force causing this to move to the left, and that force we call the applied force. So we're going to label that FAP for applied force. And then we have a force a little bit smaller, but still there, the force of friction. And again, it's the opposite direction of the movement. So left was the direction of the movement, so our force of friction is going to go in the opposite direction. Okay, one last situation. Now we have our tree, and it has a tire swing hanging on it. So we're going to bring in our box to represent our tire And it's just going to be this tire swing hanging in a tree. As always, we're going to draw our gravity. So we have our force of gravity. And we're going to have an upward force, and it's not moving up or down, but it's also not sitting on the ground. So it can't be normal. It can't be air resistance because it's not flying through the air. This time we're going to call it that tension force. So force of tension. That's an E. Okay. So this is our last situation for drawing free body diagrams. There's a lot more, and they do get a lot complicated, but what I've done is shown you the basics that you can use over and over and over again to get more complicated systems.